Hello everyone, welcome to another video on structural VAR. We talked about different theories in the last two videos. Now we'll focus on some applications of structural VAR and we'll see how the codes has improved since the VAR framework. So to begin with, the first problem is SVAR bivariate, where it suggests that consider a SVAR model consisting of the logarithm of output and logarithm of prices, in which the variables are scaled by 400 with structure shocks for U1t and U2t transpose. Compute impulse responses for logarithm of output and logarithm of prices, where the VAR is estimated with 2 lags and 1 constant. So S is given to us in different cases. First S is 30 minus 12, second S is 3102, then S11 is 3, S22 is 2, S12, S21 both are 1, so basically 3, 1, 1, 2. Then S is equal to phi 1f long run restriction, where f is equal to 3, 0 minus 1, 2, 3 minus 1, 0, 2, f is equal to 3, 0, 0, 2. So first two are short run restrictions, then we are talking about long run restrictions. Then S11 3, S22 equals 2. U1t does not affect Y2t in the short run, and U2t does not affect Y1t in the long run, so non-diagonal elements will be 0. S11 equals 3, S22 equals 2. U1t does not affect Y2t in the long run, and U2t does not affect Y1t in the short run. The non-diagonal elements will be 0. SQ transpose, where S is equal to 3, 0, minus 1, 2, and Q is given with tau 0.1 pi, so this is sign restriction. I'm sorry, this is not tau, we are talking about omega 0.1 pi, and SQ transpose, where I'm sorry, again, not omega, this is lambda. SQ transpose, where S is equal to 3, 0, minus 1, 2, and Q is given by lambda 0.2 pi. So that is so sorry, this is gamma, this should be gamma, not lambda. It's very confusing, the Greek letters, and very difficult to remember. Where gamma, yeah, sign restriction, SQ transpose, where 3, 0, minus 1, 2 is given with gamma 0.3 pi, that is again sign restriction. So this is our first problem, and hence let's focus on the first problem only, SVAR bivariate. Okay, so first things first, do we have any local functions? No, we don't have any local functions, and the problem starts with clearing the screen, where all true ls is not is, ls least all true, least equals ls all true, rm remove least equals ls all true. So by list, I'm trying to list all the elements or the index of anything that is available and graphics off. So then we might need some simulation, so let's get prepared for it, which is set seed 1, 2, 3. Okay, there is two ways. Without simulation, we could have just simply loaded the data, but yeah, we are preparing the system for the simulation in R kind Marsana twister. And then we load the data, and load Pearson, which is the data, Then comes identification method, right? Then we have the identification method, and what were the identification method? If you can, what we have just talked about is when we put 0, then we are talking about non-orthogonalization or non-orthogonalized shocks. Non-orthogonalization or non-orthogonalized shocks. Let's compare it with the question. Okay, when we select 1, where we get orthogonal shocks with short run restrictions. Then when we are selecting 2, we get orthogonal shocks with long run restrictions. Then we select 3, we get orthogonal shocks with short and long run restrictions. When you select 4, 0, 1, 2, 3, 4. So when we select 4, we basically select orthogonal shocks with sign restrictions. So basically we are creating a system, because our question is mixed up with a lot of system problems. So we are creating a system with 4 types of classes where we have no orthogonal shocks at all. So we have orthogonal shocks with short run, we have orthogonal shocks with long run, we have orthogonal shocks with long and short, and we have orthogonal shocks with sign restrictions. Then we are going to use the first bivariate. So we are going to convert our data, prepare the data for use by taking logarithm of the data, and we create the bivariate system. Very simple. So column bind, log of output and log of price, right? And we're gonna trim the first 36 rows from the system and nothing from below. The purpose of trimming the first 36 rows is we're gonna use sample period from 1970 to 2002, quarter 2. So we have a selected number of year. On the other hand, our question had more data, right? So the trim function allows us to combinedly eliminate or remove the first unnecessary years of element that we don't need to use in our question. You see, so we are doing column bind. By doing that, well, we are basically, yeah, creating the matrix, and then from the matrix we are just removing the first 36 because we want our sample period to start from 1970, quarter 1. Okay, then our question, in line with our question, we want to have our variable scaled by 400. So we are scaling our variable by 400, and then we, from the logarithm of output and logarithm of prices, what we are doing is that we are just taking the log difference, which is yt minus 1. Okay, so doing that, we are just taking the percentage differences, the percentage change, growth rates in oil, output and price, and level of interest rates. So we are taking the growth rates, the change in percentage, or delta. So in other case, in terms of equities, it becomes returns. Okay, and then we are setting our number of lags. So we are well, examining with 2 lags, because in the question it suggested have order 2, to have order 2 probably. Let me see the question one more time. Yeah, probably in the question there is no specific lags mentioned. If not, then we just take as much as we want, 2 lags, or in this case 3 lags, and 42 moving average parameter and 40 moving average parameter. Now first we need to estimate the VAR with p lags and a constant. Okay, so how do we do that? We're gonna do a loop for that, and as we remember, our lag function was lag is equal to phi is equal to, well, as we can remember, our lag was phi 1 1 minus so we had 1 minus phi 1 minus phi 1 L minus phi 2 L square, which was going like that. So for I equals 1 to number of lags is a simple lag. So we know in level we just remove the first row, in lags we remove the last. So because if it is 1 to well, number of lag is, if number of lag was 1, then the last one that will be removed is 1. If number of lag is 2, the last one that would be removed is 2. If number of lag is 3, then the last one that will be eliminated will be 3. So level and lag. Okay, so yt then phi 1 by t minus 1. So first we are fixing the yt minus 1. Yt minus 1 is matrix, which is the level and the lag, and this one was basically represented in a different way in last chapter, that we might remember. In the last chapter, what we did was, to present this problem, what we did was okay, I just need to go up. Yeah, this was the last chapter's problem. I mean, we dealt with the same situation like this. We mentioned y as y20. Here we are doing y with lags, but before last chapter this was our level, then our x was c1s, which was from the length of the total data we removed minus 2 in terms of x, which is the ones column. Then you see y11 and y02. That's how it developed. So y20 and y02, the first one level and the lag. Here the same thing is represented, but in a different way. We are putting the y thing in what we are putting the y thing in a loop, and we are suggesting, well, let's remove 1 from the first stage and up to I from the last one, depending on the lag. And y lag has, first of all, y lag has the has ones from y to first column, one column, and up to the length of y, or number of rows. Number of constant is the size of this by the second dimension. Second dimension is number of columns, right? So if that is number of columns, so whatever number of columns y lag will have, that will be the number of constants. If there are two variables, then ylag will have two columns and there will be two constants, so that automatically sets the constant. So here ylag, we are setting the first we are setting to store the data, replicate 1 number for up to y rows, and number of constant is just 1. So we are specifying, instead of using a size, we are simply specifying that we just have one constant, where this is more flexible. Then 1 to sequence of p ylag, we are doing column bind. I mean, we are mixing these two columns, ylag 10, ylag 0i. So I mean, from the total ylag we are removing the first one, and up to I is from the last one. And then our so that is our beta is x regressed on y. So if beta x regressed on y, in this case what we did here is that simply x is representing our x is representing our ylag. So ylag is basically x. You see, ylag here is simply x. Y minus 2 trimmer y1 y02. The whole thing is presented in one loop. Very simple. Ylag 10, trimmer ylag 0i. That's all. Trimmer 02. So ylag 10, trimmer ylag 0i, and number of constant is fixed. So our estimate is ylag and regressed on trimmer y p0. So basically x is ylag and trimmer y p0 is our y, right? So that adjusts with this. So yp0 and this was y0p, so the whole thing is adjusted, right? So y20, here it was y20, and this is, we are confused because we put it x as ylag. That is the only confusion. Obviously we'll put this x as ylag because we don't have x, everything is represented with yt minus 1. Okay, so basically x regressed on y. So we our linear model is when x y being regressed on x, y is being regressed on x. So y is being regressed on x, fine. Then we have mu will be 1 to number of constant rows for all columns. So basically what I'm suggesting here is that mu is just the number of constant. So how many number of constants we have, whatever number of columns we have, we'll have number of constants appearing. So that makes sense, because for each equation in the system we will have one constant, right? So if we have two constants, then 1 to number of constants, very simple, for all columns. And then we have omega v is again what y I mean yt minus 1. So basically adjusting the equation where yt minus 1, right? Beta yt minus 1. So we have beta estimate, and we represent that with the v equation, the residual equation, structural residual. So yp0 minus y lag yt beta yt minus 1 beta y lag, very simple. And so the structure residual, and then we have omega vv transpose divided by size of v, the dimension is t rows. We could have written it as the length of v, or length of v would take the highest dimension. Size of v1 is the size of the first dimension, which is number of rows. So simply we have the same thing as we did before. So yp y lag y then omega is transpose of v multiplied to transpose divided by number of rows. See, that's what I just said, number of rows of omega. Then concatenate and display. So the first stage is done. So we have defined the lag matrix. We did the OLS estimate with a loop. Beautiful. Because with as many row 1 to row, as many autoregressive parameters we have, in response to that, corresponding to that, we will have that many series, that many of, you know, y lags and x's, that will give us a good matrix. Then we're gonna construct var var matrix. Hence C1 is a long run matrix, so we need to construct autoregressive matrices from here, and this should be fun. So how did we do this part, construct the phi1L matrices? So how did we construct the phi1L matrix before, in the last chapter? It's always good to look back to the last chapter. You see, in the last chapter we did row count and column, I mean set the size of our coefficient, and mu was our way was first mu, which was, we took the we just removed 1 from, so basically we had our beta coefficient analyzed, estimated, and what we did from the last one is that whatever the total row was, from there we just, so row count minus 1. So if you had 10 rows, so 9 was eliminated from the last. So basically, in case you had 1, yeah, you know, in case you had 1, our constant was just to take 1 row and remove everything from the last. So 0, nothing from the upper portion of the vector, but all elements from the lower portion of the vector is considered, and row count minus 1 in case we have a lag 1 matrix. So our constant will be just to remain constant, will have just 1 constant on the upper portion of the vector left, and the rest is allocated for the autoregressive parameters. Then phi1 is, now you remove the constant part and column count, number of columns you have, right? So whatever the number of columns you have in your coefficient matrix, that many phis, that many autoregressive parameters you have to remove, isn't it? So everything is basically so you have 1, 2, 3. Think about a structural var, right? So what's there in a structural var? First constant, then you have lag 1 equation 1 variable 1, lag 1 equation 2 equation 1 variable 2, lag 1 equation 1 variable 3. Then the second row, lag 2 equation 1 variable 1, lag 2 equation 1 variable 2. I'm sorry, first one was lag 1 equation 1 variable 1, lag 2 equation 1 variable so no, I was correct. Yeah, lag 2 equation 1 variable 1, lag 2 equation 1 equation 2 variable 1, lag 1 equation 2 variable 1, lag 1 equation 2 variable 2, lag 1 equation 3 variable 2. That was the second column, second row. The third row is lag 1 equation 3 variable 1, lag 1 equation 2 variable 2, lag 1 equation 3 variable 2. So in case we had one lags, right? That was how it was constructed. So number of columns have autoregressive parameters. So the first column will have the first phi1 autoregressive parameter. So what we are doing is that we are adjusting by removing the first row for phi1, and from last we are actually removing number of columns, amount of information. That leaves us only phi1s. Phi2, on the other hand, now we are taking the number of columns plus mu, we are removing all, and the rest of the elements we retain, that is phi2, right? So mu is when we focus on number of rows, phi is we take all the rows, right? But we know that autoregressive parameters in one line, in one vector, all the autoregressive parameters are phi1. The second vector, all the autoregressive parameters are phi2. Third vector, all the autoregressive parameters are phi3. So, and the first one is constant. So obviously, looking back into the structural var matrix or regular var matrix, column count, number of columns matter. Okay, so all the columns, then again they are repeating. Phi1 equation 1, so phi1 equation 1 variable 2, phi1 equation 1 variable 3, phi1 equation 2 variable 1. Then again here phi2 equation 1 variable 1, phi2 equation 2 variable 2. So first we have the constants, then we have the lags, autoregressive parameters, then 1, then we have autoregressive parameters 2 for each variable. That is how the structural var columns, the var columns are adjusted. Very simple. So phi1 is column count, number of columns. The first one is removed, and number of columns 1. So how many number of columns you have? 1 2 3 4 5 1 2 3, so 4 square plus 5, 4 square into 2 plus 1. If you have two variable, 4 square, 2 square, which is 4 into 2, 8 plus 1, 9. We must have 9 columns if we have two variables, of which the first is removed, then 9, but we have actually we have actually 4 columns. So out of 8 we have 4 columns in our coefficient, right? So out of 8, 4 is reduced. Then yeah, that makes sense. Now you understand, right? That is what is done in this next part, which is exactly the same thing. When we have our beta, in beta we are removing the number of constants but nothing from the last one. So now think of, in case of two variables, your number of column is first constant, then 1 2 3 4, so you have 2 square, 4 multiplied 2 2, n square. So if you have two variables, in that n square by p, so and multiplied to 2 again, so 8 plus 1 9, you must have 9 columns. Okay, so basically you must have 9 unknown parameters here. You must have 9 unknown parameters. Then for 2 lags you're splitting that into 2 terms. So beta, number of constant, nothing from the last. K is the size of columns, number of columns you have. A is number of columns squared, obviously, because n square, number of columns squared rows, and by autoregressive parameter we have that in columns. So you see you have 9 unknown parameters. Now you remove the first one, you have 8. Now you split the 8 autoregress elements, split the auto, you actually resize them into 2 rows. So now you have 4 by 4 by 2 actually. So in the upper line or the first row you have 4 columns, in the second row you have 4 columns, 4 by 2 matrix. So 4 is 2 square, which is yeah, number of autoregressive, that is in terms of number of 2 square, n square. So 4 is 2 square, and n is obviously whatever the number of n, your residual will reflect, your residual structure residual will reflect number of variables indeed. So because for each variable you'll have one residual, so for 2 variables you have 2 residual, so you have actually 2 variables, so that is 4. And you have, obviously, if you think you have 2 lags, then 2 columns in terms of 2 lags. Very simple. So that many I'm ready to store, and A1 is the identity of identity matrix for size of V2 columns. So size of V2 columns means number of variables. You have 2 variables, so A1 is an identity matrix of 2 by 2, right? So first is beta. We are adjusting beta by removing the beta coefficient, by removing constant. Everything else is unknown parameters to estimate. K is playing with the number of columns, number of columns of the residual, which is equal to number of variables you actually have. So that is n squared by n squared by 2 for lag 2 operation, so n squared by p. And identity matrix will be created as per the number of columns. So identity matrix of k 1 0 0 1, basically to store our diagonal elements. So here how we are doing same thing, trimmer, then number of columns, we are taking number of elements, then array, we are creating to store array is zeros up when we combine k square and p, zeros, and diagonal k, A1 is diagonal of k, nothing else. So identity matrix, diagonal of k, entity of k, diagonal of k, and identity of k. Okay, so in MATLAB is identity, in R is diagonal. So now for 1 to p, that means 1 for the lag elements, 1 plus ki minus 1 to I multiplied k. So what we are doing is very simple. What we are doing here is our regular equation, which is coming from phi1 equals 1 minus phi1 minus phi2 blah blah blah. So beta coefficient multiplied to phi element. Phi element is 1 minus phi1 up until 1 minus phi I, right? That was our question. That was what we learned from theory. 1 minus phi 1 to 1 minus phi I. So 1 plus, this is the same thing, 1 plus k, whatever number of variables we have. K is actually suggesting number of variables you have. I minus 1, that is the lag parameter, yt minus 1 till yt minus yt, then I. So phi 1 yt minus 1, 1 plus phi 1 yt minus 1 till yt, I into k, number of lags multiplied to I, k into I minus 1 and k into I, very simple, to I. That's the thing. 1 plus k into I minus 1 till k into I. So then for all rows and I mean autoregressive columns, autoregressive number of columns, we put whatever we estimated from our beta. Our beta has been estimated earlier already with regression, and from the beta we are restructuring the beta for I yt minus 1, beta yt minus 1 till beta yt, and whatever results we have, that is represented in an index, and we are taking all the elements and adjusting them as per all rows to up until I columns, so that they are structured well. And then so I see, I mean combining combining CTMP. CTMP actually means all elements. Wow, that is something I didn't know. CTMP is all elements representation. Okay, this is as it is. Now this part, reshaping, that is this beautiful usage. What is reshaping? It is reshaping as per Gauss suggestion, reshaping your matrix in a way so that it is represented as we want, which is we're actually wanting our matrix to be reshaped. What is A1? A1 is, okay, so you have 2 by 2 matrix here, 2 by 2 minus, okay, so, and reshaping, right? Give me 1 second. I'm not sure how to explain this. So basically you see this matrix A was taking storing all the elements of what we have of beta, because it was taking all the elements of beta and its lags, is dimension. The question is dimension. Its dimension is non-squared. This is a square matrix. We want this to be a square too. I mean we want to take 1 minus, so basically we are just adjusting. We are taking 1 minus A and all the elements we are basically taking 1 minus all the elements here we estimated, and we want to take a difference with 1 and we want to store it in A1, which is our lag, first lag, because what is lag? Yt minus Yt minus 1, that is the difference, right? So the thing here, Yt minus 1 of beta, the dimension is adjusted here. So if we do 1 minus that from constant, we actually remove that, we should get our phi1 parameters, right? Because 1 minus phi1 L minus phi2 L square, that's what is the equation is. So 1 minus phi1 L minus phi2 L square, this is your 1, this is your phi1 L, right? But this is a square matrix, so this should be square too. So how can we do that? We take this matrix and we reshape it by to represent as a k by k matrix, and k is, as we know, 2, so it will be 2 by 2 as it is. And before this step was to estimate A, which was Yt minus 1 representation. That's all. So yes, very simple. Yt minus 1, then we take all the elements stored in A and then we reshape it so that 1 minus phi L, 1 minus phi 1 L by 2 L is calculated with that, right? L, this is L estimation. How is this L estimation? Lyt is equal to Yt minus 1, that is what we have just done here. Lyt, this is our Yt, Lyt, Yt minus 1. So Lyt equals Yt minus 1, or when you do Lyt minus Yt minus 1, you have Lyt2 or yeah, that's what is TMP. Now we need to invert our autoregressive parameter to use in moving average, because now we want 1 plus psi 1L plus psi 2L. So we want to represent that for moving average. For the moving average, we just we are inverting. Now let's get back to identification. If our I type is 0, that is non-orthogonalized with 1 unit impulse response, according to the question, we have S1001, right? Yeah. If there is, no non-orthogonal unit impulse response. Else if I type, beautiful, the equation is exactly the same. Oh, this reshaping can be done very easily in R with just creating the matrix, that all, nothing else. So you're saying create a matrix with k by k, that's all. We don't have to call for a reshaping here. So if I type 0, start the logic here. S is equal to matrix by combining 1001 k square b. Combine 1001, number of rows by row is true, so by row is true, number of rows is 2. So the matrix is the by row is true, means the titles are by the rows. So you have 2 rows, and we are setting our matrix by created by row. We can create a matrix by taking elements from columns. If we do by row false, then elements will be taken from the columns, but we are taking we are setting the matrix to create it by row. So 1001, if we have taken columns, then it would have been probably different. So instead of 1 0, we could have 1 0 and then 0 1, right, like that. But we are creating 1001, so taking elements and placing them in rows, number of rows 2 and by row is true. Else if I type is 1, that, if you can recall, we set this condition first. Orthogonal one standard deviation impulse response from a short run restriction given to us in the question 30 minus 1 2 s is equal to phi 1 f, right? Short run restriction, so s is equal to 30 minus 1 2. Orthogonal one standard deviation impulse response based on long run restriction when I type is 2, which is s is equal to 3012 minus 1 2, then that is multiplied to phi 1, which we have already calculated a1. It is multiplied to phi 1. Beautiful. Then I type 3 orthogonal impulse response based on short and long run. So what do we have here? We have S113, S22, S112. In our question is given to us S22, S121, S210. Another diagonal element is S22, which is phi 1, A1 inverse phi 1 minus phi 1 divided by phi 2. That is, this is coming from, just give me a second, let me open it up for you. So that particular representation is coming from here, phi 11, phi 12, S12, right? So you see, phi 11, phi 12 multiplied to S12, and we have a negative sign as well. Good. So that's how we represent S22. So orthogonalized impulse based on short and long is this. So in that case, we create this S, and orthogonal impulse response based on sign, and sign is S given to us 30 minus 1 2, theta is equal to pi 0.4 because omega is 0.4, and cosine theta minus sine theta cos theta. SQ is equal to SQ mat, which will rotate SQ transpose, Q matrix transpose. So this we have set our identification, because basing on this we'll do our identification. Beautiful, right? And then SSQ, and I'll just come back to our problem now. So up until now, what did we do? To be very precise, very quickly, up until now, first portion is to represent transfer, use our y and x. Using our y and x with a loop, we have estimated the beta coefficient, and yeah, and from estimating the beta coefficient, very simply we did that, and doing from there we estimated our phi 1, which is phi L 1 minus phi 1L 1 minus phi 2L, that is with another loop. And there was something to remember. It was a bit difficult because we are for the first time we're trying to do this with a loop. The first step, the thing phi 1L had two stages, because autoregressive parameter itself L equals yt minus 1. So we needed to identify that first, which was L was being estimated for yt minus 1 up until yt. So our beta, we put, if you think up from yt minus 1 up until yt is a house where it or arrays where we will fill those with our beta parameters, estimated betas. We just placed them inside, and then we did 1 minus phi 1L to find phi L. So that was a bit difficult, but it's easy to grab when you continue to follow. And then we just did invert to use for maximum likelihood for moving average estimation, or to use for maximum likelihood estimation. And then We are setting identification, second stage, and then there comes the next part. Now we'll use our autoregressive parameters to represent our moving average parameters. Again, we need identity, because 1 plus phi1l plus phi2l, that's how it will grow, because psi1l plus psi2l, because we need to estimate psi l. Psi l equals psi1l 1 plus psi1l plus psi2l up until psi n psi q up until psi q lq, l to the power q, psi1l plus psi2 l square up until. So that's how it is. So we have an identity matrix of 2 by 2 number of variables adjusting to number of variables, and all the elements are from there. We take all the elements in our moving average parameter. So C is simply column bind the diagonal elements. So all the elements are stored in C in the 2 by 2 matrix. For I equals 1 to Q, first we have zeros. This is just to store our data, SS, where this data will be stored. J is 1. Okay, so we have 1 moving average probably. So we'll use a while loop. Okay, because we're gonna use a while loop, we're setting the J to start from 1. Okay, J is up until J is less than or equal the minimum of autoregressive parameters and the lags, P rows and I columns. We take the minimum, smallest elements in each column. So J, while J is up until J is less than autoregressive or equal, because the moving average parameter here will not exceed the autoregressive parameter, P rows and I columns, the structure. So SS is 0, CKK, where I mean you are putting zeros in SS in the as the dimension of C, which is a square matrix. J is 1, well J is equal to minimum of C. Pi the structure, referring back to the structure. SS is equal to first SS, which is a 2 by 2 zeros, 1, which is SS is 1, plus reshaping. Now we are reshaping A to be 2 by 2. J is equal to all rows J columns. I mean for just 1 we are taking, and then we're taking C. So we're taking A, all rows J columns. J is 1, first column, multiplied to reshape. So psi 1 L, right? This is psi 1. Psi 1 is the first, J is the first autoregressive parameter, reshaped. Then L is lag, I minus J plus 1. So I minus J, I was moving average parameters. So the what happens is that we have to understand our, we have to remember what is our moving average equation is in reduced form. It was I equals 1 to J, right? So I equals 1 to J psi phi I L psi I L, right? I equals 1 to J psi I L, right? I equals 1 to J, yeah, I minus J plus 1. Okay, so I minus J plus 1 and A. A is our moving average parameters. Psi I, basically that is psi I because this is inverse already. This is something we need to understand slightly. Okay, while it seems a whole lot of confusing, it is actually not, because we need to remember the equation that we were dealing with. The equation was, it's better I get back to the equation and show you the equation. The relationship between the moving average parameter with the autoregressive parameter was here, right? Where psi I is first with psi, our moving average parameter starts with identity matrix, which is psi naught, which equals identity matrix, the first element, always identity matrix. We mentioned that. Then, as you can see, I plus 1, psi 1 I to the power I is equal to minus 1 I plus 1. So that is the element that we need to remember. So when we take this on the other hand side, what do we are left with? We have phi 1 representing psi 1, which is the same thing. Then we have I plus 1. So this is the thing, this is the equation that is actually represented what we are discussing currently in that part. Or yeah, you see, how did we do this in our VAR equation? How did we estimate our moving average parameter in the VAR? We might probably want to have a look into it. Okay. So in the VAR, you see, we estimated our equation very simply in the VAR chapter. Then we used that simple A's to construct B, and we played with B, right? We played with B, and it's better we go talk about one specific equation where we transformed our parameters with this psi 2 equals phi 1, then psi 3 phi 1 psi 2 plus phi 2, right? So you see, phi 1 multiplied to psi 2, because the equation was the relationship between phi 1 and psi 1, as I have just shown you, is phi 1 I minus 1 I plus 1, minus 1 to the power I plus 1. And the transformation is psi h minus 1 to the multiplied to s, psi h minus 1 multiplied to s, right? So this is what we are doing here. In fact, this is the psi 1 portion, right? This is our psi 1 portion, where what we are doing here is that we're gonna make use of our phi 1 estimate. And the psi 1 portion is, first you bring in the phi 1 estimate, which was a, instead of h we are doing j, which was in terms of h we had what? How did we represent? Psi h minus 1. So this is psi h minus 1, nothing else. So you have the psi representation as psi h minus 1, right? Impulse response function. So so this is our representation here. And what did we do with our impulse response function? What was the impulse response function? Impulse response function was psi h minus 1. This is psi I 1 to the power I, psi I 1 to the power I. So phi 1, psi 1 to the power I minus 1 to the power I plus 1. So this is 1. C is 1. minus 1 to the power I plus 1, minus 1 to the power I plus 1. Let's revise one more time. Psi 1 to the power I minus 1 to the power I plus 1. So psi 1 to the power I, because this is the initial one, I naught, then psi 1 to the power I, and psi 1 is starting from j kk square matrix, just like phi 1, psi 1 to the power I and minus 1 to the power I plus 1. Minus 1 to the power I plus 1 is you are taking one's matrix, all rows, and you are doing I minus j plus 1. I minus j plus 1 columns. Beautiful, right? J starts with 1 and j ends up until you reach the number of elements equal to autoregressive parameters. So j, while j, as long as j is less than or equal to the dimension of pi, p rows and I columns, SS's size are not I naught, then I1, psi 1 will grow with this, is psi 1 I, which is basically phi 1 I, which is phi I, same thing, multiplied to why is the same thing? Because we have already converted this to, we have already converted in, taken inverse of a1. Okay, now we don't need it. Right now we can gonna directly use that. Then psi 1 I to the power multiplied to minus 1 to the power I plus 1. So identity matrix I minus, this is doing the conversion part, I minus j plus 1 represented with kk. It seems a bit difficult, but it is not actually. It's a very good thing to remember and to practice again and again and again. So phi 1 I, psi 1 I, and this is the plus minus thing, minus 1 to the power I plus 1. Then j will update j plus 1 up until it reaches the dimension of moving average autoregressive parameters. So what was autoregressive? Autoregressive was yt minus 1 k I minus 1 to k I mean yt minus 1, it will go on up yt minus 1 or yt minus I. So this is I, it will go on as an up until I. We take all the elements, we have the ones, then 1 minus phi 1l, 1 minus phi 1l, I, phi 1l to the power I, so I, and this is 1 plus psi 1l to the power I, psi 1l, which is basically phi 1 I equals psi 1l I, they are the same thing, multiplied to the sign I minus j plus 1 kk, and that updates. Beautiful. And then we have that we take the transpose of this thing, our representation, we take a transpose of our representation, and C becomes all the elements of this and constant and all the elements of this, that's all. So C is not constant, I'm sorry, C is simply, this is how the whole thing will grow, because each time we have SS, each time SS will continue to grow. So 1, and this is C, which is 1 plus and TMP. For moving autoregressive we don't have that. For moving average we have 1 and that once, because psi naught is 1, the first one is identity matrix, nothing else, then it goes on. And then comes the impulse response function, which is psi h minus 1 multiplied to S. We take the vector of S transpose. What is S transpose again? What is S here? Okay, S is our identifications, right, that we are gonna use. orthogonal impulse response function. So we have S, which are our identifications for I is equal to 2 to q plus 1, because psi h minus 1. So S is equal to the impulse response will grow as summation of I 1 to h, I equals 0 to h minus 1, or I 1 to h, right? Because that's what we learned in page 2. Impulse response is psi h minus 1 to s multiplied to s, right? Or I0 h minus 1, or I1 I equals 1 to h. That's how we grow. So if I equals 1 to h, then this is 2 to q plus 1, obviously, because I equals 1 to h means depends on the number of lags. Okay, we have 2 lags, so it will start from 2. So 1 means here number of lags, because here is h minus 1 lag. If that was h minus 2 lags, so 2 to h, here in this case 2 to h is q plus 1. Why h is q plus 1? Is q our moving average parameters? Yes, because h is associated with moving average parameter. Okay, psi q, you see, psi h or psi q. So h minus 1 is the moving average parameter. So actually rho to q. So 2 to q plus 1, h plus 1, h minus 1. So this h minus 1 was q. Now h is, if h minus 1 is q, h is q plus 1. Very simple. H minus 1 was q, so h is q plus 1. Q plus 1. I2 to q plus 1. And what we do is that we take s and we multiply s with psi h, right? So again psi, we take that portion. Psi I c, which is our moving autoregress moving average parameter, ci, because c has stored our moving average. C is representing our moving average. So all rows up until I columns and kk, so you're representing that in a matrix, multiplying to s. So we have what? We have our impulse response function. So impulse is stored as impulse and all the elements of TMP. Impulse, the first impulse is generally stored as, impulse and all the elements. Okay, that's how the matrix is created. First is impulse. Impulse was S in vector and the elements are in vector. Impulse response function, elements are in vector. So orthogonalized impulse response function give you impulse matrix. Column bind. So this is what? This is moving average up until I, will grow up until I, kk, that's all, multiplied to s. Simple. And then we have impulse, and then we take the transpose of it. So rows and columns are just changing. It really doesn't matter much. It represents, if you just plot impulse, you just want to change the plot, that's all. It is just for plotting. It will help you with plotting. So impulse, column bind, C, TMP, the dimension we need to constantly change because we did a transpose here. If we didn't do a transpose here, we never had to do a transpose here, and this transpose was not essential at all because S is transposed here. Again, why S is transposed here? There is no basically good reason to do that. You're just vectorizing it anyway. Orthogonal impulse response functions. So as we had just vectorizing our S, it really doesn't matter, does it? Let's think more clearly. If we have, like in the question, if we have 3 0 minus 1 2, and if we transpose it, it becomes 3 0 3 minus 1 0 2. So if we take just the elements, then 3 0 minus 1 2 gives you 3 minus 1 0 2. All right, that's why we transpose, because if you are taking elements, then you get 3 0 minus 1 2. Instead of that, you get 3 minus 1 0 2, but you want 3 0 to be together. So if you do transpose, then 3 minus 1 0 2 is the structure, and when you do take the elements now, you get 3 0 minus 1 2, just as the order is maintained here. So it is important that we maintain the order of S. It is the same reason why we are taking transpose of this and transposing it back, because when we are doing transpose, we want doing transpose and then taking elements, make sure that your elements order is maintained. Okay, so you're not taking one element from the first equation, one element from the second equation, then again one element from the first equation. No, you're taking all the elements from the first equation, then you're taking all the elements from the second equation. The trick is convert the matrix or transpose it, then take the elements. Then when you take it, transpose it back, you get as you wanted, just like before. Beautiful, beautiful, beautiful. This was a very confusing thing for me, and now, yeah, beautiful. So you have impulse response function, and taking a cum sum or cumulative sum, here we are using apply function. Apply is x margin fun. So x is impulse, margin is 2 because it's a 2 by 2 matrix. Function is cumulative sum, x margin fun. Beautiful, right? X margin and function. Cumulative sum, you're doing adding all the impulses of 4 levels. 2 by 2, you're doing it by 2s or 2 seasons or 2 quarters or whatever it is. So that is problem 1. Quite a lot of things we learned. We learned how in loops we can convert our autoregressive and moving average parameters. So first stage, we have to look into yt minus 1, and the relationship is important between yt minus 1. We have seen good use of identity matrix, how we can use the identity matrix to actually change the dimension, that is determining factor in identifying our autoregressive and moving average matrices. Then we see that how we are calculating the autoregressive matrix first, and then we use the autoregressive matrix to beautifully estimate the moving average metric, and moving average metric is used again for impulse response. And then how we can twist the impulse response function, and taking the elements, how we can actually get to our a complete impulse response with the constant. So basically, when you take transpose of a matrix, you are preparing to take index in proper order, because when you without transposing, if you take orders, you'll have one element from first equation, one element from second equation. You don't want that. You want all the elements from first equation first, then you want all the elements up from the second equation first. So beautiful. You do that with transposing it first, the matrix, the main one, take the index, then after calculation you can just transpose, giving it the matrix structure, you can transpose it back and you have the previous matrix. That is a very good example of controlling matrix dimension. So that was the first equation that took us a long time, but it was the base of very an advanced econometric technique. So we'll move into the next example. But hey, I need a cup of coffee, so I'm gonna pause it here and grab my cup of coffee. Thank you.